faccio vedere. Right, so today is the fifth class. Yes, we will see. We will. Yeah, right. Last time we started with EDF scheduling. We started with the all problems with feasibility, sensitivity. Yes, they are going to change the materials. And today we will enter a bit into more the design problem. So again, we are again with this condition. And we are considering what is the space of feasible computation time. So in this case, we assume to have that all periods and headings are known, and we wonder about what is the space of feasible computation time. So the condition is always the same. We have that the task set is scheduled if and only if the implementation is less than 1 and the demand function condition is true. With t into a set of deadlines less than equal to d star, some d star. If we are changing the computation times, then we cannot assume, we cannot exploit the upper bound in the DBF to compute a short of d star, so we have to play with d star, with the bigger d star, with d star raised to the upper period. And so for given ti and di, then what we can observe is that the space of EDF scheduled computation time is convex. Why is convex? It's convex because it is the intersection of half spaces. So one condition of this for one value of t is a linear inequality, because if you assume that t are given, so basically small t lives in a set which depends on periods and deadline. So this is known. This is then known. Then you have so these are known. No, this is just coefficients which are all known. Okay, and this is a linear inequality. So the variables in this case are the computation time. So for one value of t, this is a linear inequality. So it's a convex. It's a half space. And if you are doing for all t, basically you're making the intersection of many half spaces. Since one half space is convex, intersection of convex is convex. So this, I mean, just from this condition, we can already say that the space of feasible computation time under EDF is convex, which is already something that we can use for optimization. This is just an example. If you assume that the periods are 4, then 5, periods T2, 6, and then D2, 5, then the space of absolute deaders that needs to be checked are these ones. Okay. So if you write these in terms of there is let me see if there is a mistake here. Right, so I can equivalently, we know, yeah, here what I do here, since I want to write the condition of the utilization, basically I write UITI, I write CI as UITI, and so TI, I put it in the coefficient, and UI is the variable, okay? So basically this is the coefficients that you get from one point, from the point 5, multiplied by TI. So basically, at point 5, you get, okay, look, you have deadline 1 is 5, deadline 2 is 5. So at point 5, you get 2 jobs. One job of the first task and one job of the second task. So here in the DBF, in the coefficient, you would have 1 and 1. But since I'm multiplying by the periods here, and I'm writing utilization here, so I have just T1, T2. T1 is 4 and T2 is 6. So here 1, 1 translates into 4, 6. This is just to express the same condition as before as a function of utilization. So no big mass, okay? And here we write the point which is 5. So at 9 we have, I mean just reading not all of them, but just to see an example. At 9 we have 2 jobs of the first task. In fact, 9 is the second deadline of the first task. So we have 2 jobs. So we have 2 jobs and 1 job. So since the period is 4, then 2 times 4 is 8, so we have 8, 6, and 9 is the time that you have to check. You do this for all deadlines up to here, okay? Then this condition is just the total utilization less than 1. Coefficients 1, 1, 1. So this is just the necessary condition for EDF. And this very last condition is just the non-negativity of population. So you have minus 1, 0, and 0, minus 1, 0. Okay? Just to say that you can write the space of feasible utilization as an intersection of linear inequalities. Very easy. Yes, here I basically draw that example. I think it is that values, okay? And you have, right, you put the space of utilization, you have that values, and that's it. I mean, basically, that's no big deal. It's just, drawing equations. I mean, maybe it's worth noticing that, right, so the total utilization equal to 1 would be like this constraint, which is almost the exact constraint. So this is almost necessarily sufficient. However, here you have another constraint, which is this second constraint. Okay. And here, I mean, what we observe is that there are many constraints that are somehow useless, okay, but that we don't know how to discard. So this is something that is not so clear. I don't know, here maybe. Actually, I think we cut a bit. I think this constraint also is doing something useful. I think this constraint is also cutting a bit. Yes, in fact, let's see. So what I wanted to say is that from the previous drawing, we see that instead of the 5 constraints that we needed to, well, basically before we had how many? We had 7. Well, we had 5 from the deadlines, plus 1 of the utilization, plus 2 of the non-negativity. So 5 from the deadlines and 1 of the utilization. So basically here from the 5 deadlines, we get only 2. I mean, the relevant ones are only 2 in the second deadlines. Okay? So yeah, I'm here also write those values, 5 and 17. Maybe let's go back and go. My guess is that 5 is this one. Yes, this one, because this goes to 5. Yeah, so yeah. Oh no, this is anyway, I think that's the one corresponding to 5, the one corresponding to 5, and the other is the one corresponding to 17. Or maybe the other way around, I don't know. So what I'm saying is that it is necessary, sufficient, we don't lose anything, if instead of considering the entire set of deadlines, we consider only the deadlines 5 and 17. Okay? I mean, this method that I did somehow graphically is maybe nice, and actually I've implemented it a bit into some code, which allows you to prove many deadlines. And in practice, you see that the number of deadlines that you really need to consider without losing anything. So with the same equivalent test is about of the order of the number of tasks. So let's say if you have 10 tasks with ugly periods which would require you to test a huge number of deadlines, in the end, the number of deadlines here is in the order of number of tasks. So if you have 10 tasks, maybe you can have up to 15 maybe deadlines, okay, which is a big reduction of the number of sets.
What about the worst case? That's the average case, right?
The average case of what?
For the number of deadlines. I mean, can you say that in the worst case also the order is around?
Yeah, but here it's hard. Okay, I did not prove anything. I mean, here we're talking about just experiments. So I even have difficulties to worst case. I mean, what you may mean with worst case is can I construct a task set such that all deadlines are always necessary and sufficient? I don't know. Okay. Right, so what I'm saying, yes, of course, optimal computation time. So let's say that you have the problem of designing DMPEG decoder, whatever desired problem you have, in which you can play with the computation times, in which the computation times are the variable. If you use EDF, we have a good result. We have something which is good for optimization, because the exact region of EDF schedulable computation time is convex. So we can apply convex optimization, which is going to be very efficient, to solve more efficiently the problem of designing the computation time for a given period of deadlines. Okay? This is something that is already somehow helpful. Okay, now we enter into the typical big mess that we find when we start to play with deadlines. Yes, why is the problem? Because we cannot say, so this was the condition of the DF. Again, deadlines and periods are inside the floor and are into the set, so we cannot play as nicely as we did with this condition. We cannot play the same way for deadline, so we have to find some other way. Okay, first I want to have some qualitative analysis. Let's go into this. Let's go into this very special case. Okay. So let's consider this example with two tasks, so n equal to 2. Okay, we are wondering about what is the space of feasible deadlines. Okay, so we assume that computation times and periods are given, and we want to see what are the feasible deadlines of the DDF test. So okay, so we have two dimensions. So we have D1, D2 in this case, D1, D2. Can you see, or there is some reflection? Can you see somehow here? Okay. Okay, let's see. Okay, two tasks. Let's say that we have equal periods. A super special case. Periods equal to each other. It means that they are equal to each other, right? So that they are activated here at the same time. So the worst case is when they are both activated at the same time. So we have P1, P2, which is equal to P1. Okay, and let's also go into the case of total utilization less or equal than 1, of course, which means because if it's more than, which basically can be translated here as C1 plus C2 less or equal than T1, which is equal to T2. Right? So we have, let's say, here we have to fit C1, and here we have C2. And here it is correct, because I mean, these periods are the same. Now, the question then is, what are the feasible deadlines? Feasible deadlines are quite, well, I mean, it's written in the slide, but just try to think about it. So, how can the deadline be reduced as much as possible? D1, D2. Okay, let's do this. My guess is that D1, D2, let's say that I move them together for the moment. They certainly can be moved both up to the point C1 plus C2. Because if you have D1, D2 here, D1, D2 here, it is something you can certainly do. So let's say here at point right, let's say C1 is what? Something like this, and let's see, do something like this, and then we do C1, C2. Oh, so this point is the point C1, C2, C1 plus C2, C1 plus C2. So the data can be here, okay? And of course, as usual, because of this sustainability notion, bigger data are always fine. So if this point is good, also here is good. Okay? Everybody try. Ah, yes. So this point is good. So this point we said it is C1 plus C2. It has both coordinates C1 plus C2 and C1 plus C2. Okay. Now listen, from this point, can I reduce any deadline? Can I reduce any deadline? What?
It could, depending on how you.
One. Can I reduce one deadline?
Yeah, the first one.
The first one. Right. I can reduce the first one down to C1. And it is feasible, right? It is okay. So I can reduce D1 down to C1. Okay, this is something I can do. And of course, as usual, when this point is good, also everything here is good. Okay? But then I could have done the other way around. I could have kept D1 here and then reduce D2. Because if I do it, let's say, this way, then I have, this is, I mean, the point is that for EDF, ties are broken arbitrarily, right? So I can play with this arbitrarily, with this, let's say, possible, degree of freedom to change the data which I can reduce. So basically, from this point, I can certainly go down to C2. Okay? So basically, this point has coordinates C1 plus C2, C2. And these points have coordinates C1 and C1 plus C2. Okay? I can write it here. C1 plus C2, C2. And this point is coordinates C1 and C1 plus C2. Okay, and then I cannot do well, just now, for the moment, just believe me, okay? But then this is the space of the exact feasible test. So you cannot do anything better for this super special case, of course, with n equal to 2 and equal to this. In general, and now I can, I can do it. In general, so let's see what did I write. So we can reduce D1 to C1, but then I have to keep D2 equal to the sum. Or I can I can set D2 equal to C2, but then I need to leave D1 to the sum. Okay? Also something important, the convex combination of these 2 points, so let's say I know that this point is good, but this point is good, a natural question would be, are the points in here good? The data over here good? And I would say no, actually no. Because what does it mean? It means, let's say I have data here. If I increase one and reduce the other in this way, are those deadlines feasible? Not. Because at least one of the 2 deadlines has to be C1 plus C2, because that's the same, right? So, these points are not good. Right. More in general, if we assume that we have all the same periods, and we have to have, of course, feasibility, so total utilization less than equal to 1, for any permutation of the indexes, then a vertex, I call this like a vertex, has coordinates where you just, the permutation just decide what order of decreasing the deadlines you use. So for any given order, you set, let's say, the first one, the pi 1, is the first of the permutation, you set it equal to C1. For the pi 2, you set it equal to C pi 1 plus C pi 2. The deadline of pi 3, C, and it is just, the mathematical way of expressing exactly these conditions. So basically, you have for n tasks. So here you set the deadline d of pi 1, the one with the shortest one. Then you set the other one at d pi 2, which is the sum of this plus its computation time, and so on and so forth. Okay? This is just the formula of this. Okay, any question on this? Fine. Okay, now how do we make that reasoning more general? Well, we need to introduce yet another way to see exact schedulability. Why do we need that? Because, as I said before, these periods and deadlines are inside the floor of the DBF condition. We cannot, it's unfit, that condition is unfit, we cannot use it to find a space of feasible periods and deadlines.
That's Bing, right?
Being the periods. Now, being the periods and deadlines into the set, blah, 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 blah. And I think it's being. I mean, since the.
Okay. That's okay.
Being the periods. Then we have this theorem, which is somehow crazy, okay, as you know, this kind of strange things. But then I'll try to prove the equivalence of well, I'll prove it now. The equivalence between the DBF condition and this condition. So this condition is somehow it requires that. I mean. Yeah, this. So for all possible vectors of integers, except the vector with all zeros, this is out of all the integers, okay, vectors of all the integers, except 0. So for all these vectors, we need to, so the task set is scheduled if and only if, okay, for all blah blah, we find an index among in IK. IK basically is the set of all integers in K that are non-zero. So, for example, let's say I take vector equal to 1, 3, 0, 5. This is one value of this. Okay. I need to find if it exists I in what? So this is 0. So I discard it. So this is in position 1. This is position 2. This is in position 3. In position 4, right? This is just the position of the integer into the vector. I need to find if it exists I into 1, 2, 4, so I'm not checking at 3 because at 3 is 0, such that this condition is true. This condition, if you want to look at in a sort of well, basically represent here this integer as such like number of jobs. So you see, this is sort of the demand, because here you have number of jobs times the computation time, and this has to be less than this is the absolute deadline of the I task, the KI job. So this is the KI. The absolute deadline of the KI job of the I task. Okay? Just as I'll prove the equivalence formally, so I'm at least, I mean, I didn't try it before, so let's see if I don't make any mistake. If instead of clarifying, I make bigger chaos. So now, from the DBF, now I'm proving just that from DBF, the DBF implies this. And then the other, you know, you do yourself or give a reference. So how it works? So if the DBF is this, for all t greater than 0.
But isn't it obvious that the DBF implies this?
It's obvious that the DBF, well, if it's obvious, I'm fine, not proving anything. For me, it's obvious. No, it's obvious. Right, no. It's obvious. If it's obvious, then you ask Abby why, right? It's not like okay, so why it's obvious, right? So for all t greater than 0, we want the, I mean, what do we know? Because we know that the DBF is true, right? Max between 0 and t plus ti minus ti Yes, I hope I didn't make any mistake. Ti plus and minus, yes, because always, yeah. Okay, this is the DBF for all t, the sum, number of jobs, computation time less than the point. Okay, we want to prove that this implies this. Okay, obviously. Okay, so what does it mean? It means that, what does it mean proving this? It means that, I mean, let's say that for all k, we have to find an I, possibly using this hypothesis. Because we have this. We have this and we have to prove this. So in the end, we have to find I for a given k. Okay, so the enemy give us a k. So we take this k, which is a vector of k1, k1, k2, kn, okay? And we know that they are not all zero, at least one non-zero. There is at least one non-zero because of this, right? So the k that is given to us, there cannot be all zeros. We have to find I. Okay, so first I define the deadline D. Let's see. Let me define the deadline DI, or let me define DI. Okay, then we'll see as right Ki minus 1 Di plus Di. I define this. Okay, we are given this. I can compute this. No surprise. And then I define our nice guy, the candidate I, equal to what? To the argmax among the k I different than zeros of the I. Basically, I call I star, I mean the candidate I, because I mean the goal of the proof is to find I, right? For all k, we have to find I. I define the I like the absolute, interpreting as the absolute deadlines, and then I define the I star, the candidate I star, the candidate I that I want, as the argmax, the value of I, among the one that are non-zeros, the one where the DI, the relative DI, is the largest. Okay? Is it clear? This is just, you just have to believe it, and then we'll see that this I star is the good one. Let's simplify that. Okay? It's clear at least how I do it. Why, we don't know. It's magic. But at least how, I hope it's clear. Is it clear how? Okay. And I can always do, because this set is not empty. This set is not empty because of this hypothesis. Because the ki are, at least one is non-zero. And since at least one is non-zero, this set is not empty. Otherwise, if they are all zero, then this set will be empty. But then, I think because of this hypothesis, this set is not there. Okay, so why this I star is good? So now, by the way, we didn't use yet the DBF condition. We have a big, powerful guy that we want to use. Right? Okay. Right. Okay, let's see a second. Now we have to prove this. How is the proof? Yes. Okay. Okay, so we have to prove this. Okay, we have to prove this. Very nice. So what do? We do as follows. The sum for j. Okay, let's use j, and I think with I here, and it's j. Just to, because I is the one that exists, and j is like the running index. Okay, j that goes from 1 to n of those values, those k, j. I have to read the proof. I mean, better to do it properly than do it in more chaos. The chaos is always. Let's take a look at before, but then I forgot. No. Yes. Allora, now it's vabbè, quello cos'è? Se maggiore vabbè, poi viene da 6. Io quello viene da 6, vediamo. Vabbè, it looks like it should work. Okay, so the idea is to exploit this property for t equal to di, for that for the d computed with this di. We know this to be true for all t, and I say, okay, let's set t equal to di for the I index of that value. Let's see what happens. Okay, what happened? Then, from the DBF condition, we know that the sum for I from 1 to n of the max between 0 and di plus, now the sum is on j. J because I is a special index that we have taken. Yes, equal than di. Okay, that's what we know. Okay, so we know this. We know this because we know the DBF condition, and we know that we know it for all t. I mean, unless I made a mistake in replacing di in t, we know it. Okay. Okay, so I want this to become this because this is what we want to prove. It should be not too difficult. Because, okay, the right-hand side is easy, actually super easy, because it's already what we want. Because the right-hand side is di. But di is exactly this. Exactly ki minus 1 ti plus di. So the right-hand side is gone. Let's see what happened at the left-hand side. What happened? Allora, un pochino. Max, since it is the max, perfect. Okay. Right. So that's the. I give you the idea. Okay, I don't need the DBF anymore. Yeah. Basically, what over time, so it's nice over time. So what we did is that, okay, this is time. We took di here, okay? Di is the absolute deadline of some task. So some task here, the I task, has an absolute deadline here. The other tasks are here doing their own stuff. Because of this choice, since then the deadline, the last absolute deadline of the other tasks is always on the left of this line, because the I was the max, right? I was selected as the index that produced the maximum and the maximum dj. So the others, the other deadline is always less or equal than the other, the max over here. So these are all the deadlines of the key. No. So these are the deadlines of the k J job of tau j. Okay, so the kj deadline or or if you want the deadline of the kj job of tau j. So this is the deadline, the absolute deadline of the kj job of tau j. Okay, these deadlines are always less or equal than the I. Okay, because of this construction. Okay, so how much demand do this job create into the interval 0 di? How much does any job tau j create into the interval 0 di? Kj Cj, here we go. So this term is exactly, is literally equal to that. I mean, if you want to do, yeah, I mean, let's see if I can do it in a cleaner way. Yes, I can do it in a cleaner way. Right, so this is certainly larger than the sum for j. Yeah, I do it in a clear way. Once in my life, I do something in a clear way. Max 0 of d. Yeah, I want to do this. Yeah, j. Yes, j plus dj minus, yes, plus dj minus. This is okay. This is a key step, and then I will arrive. I explain, and then you understand, and everybody's happy. Okay, look what I did. Basically, this is always larger than replacing this di with this, because this is because of the choice of di. This is always smaller or equal than di. This is the absolute deadline, the kj absolute deadline of the task tau j. Okay. See, because of this choice, I can always go down. I mean, this is below this value. So I say I write this inequality. Okay, and I can replace here. But look, here the magic happened, because dj goes, the minus 1 and the tj goes, tj go, kj is integer, the floor is going, the max with 0 is the max with 0 is go, kj. Okay, everything goes. Okay, and so we have proved. And this is one the proof in one direction. The proof in the other direction will use your own. I mean, it's a kind of the same. I mean, if you want to do it as an exercise, I just give you the key observation, and then you can try the math yourself. So the other way around is that, now we did a proof. I proved that from the DBF, this follows. Now we have to prove that from this, the DBF follows. So to prove the DBF follows, we have to prove that for all t, the DBF holds. Okay. The key thing is, I don't remember. I tell you the key. Implication. So from there, you know that. Okay, we build this mapping. The key is to build, I mean, for all T, we have to prove, yes, we have to prove the DBF condition. So we build the mapping that from T, we build the integers. K1, I mean, the usual, K1, Kn, where you set Kj equal to the max of 0 of t plus tj minus tj tj. Okay, so this is basically, and then from this mapping we see that, you know, one condition mapped to the other. So if you want to do yourself, you just use this mapping and you go. Okay, now that you are maybe confident that this condition is true, and then basically this condition is equivalent to the DBF condition, let's see what is the implication of this condition into the space of periods and edges, which I remind you was our initial goal. Okay? Okay, basically, this can be seen as a covering problem. We have to find, what do we want? We want it for all, let's see how it's a covering problem. Let's draw for two cases this set, the set of all integers of vector except 0. All the integers, right? Basically, what we want is that here, if you write this for I that goes from 1 to n, you have n, in this case 2, n is equal to 2. You have two half planes, okay? Basically, covering problem because you are requiring those two half planes to cover entirely this set. Because if you cover entirely this set of integers, what does it mean? It means that for all integers, you have one condition which is true for that point. Okay? Let's say I find the two half planes that are like this and maybe this. Okay? So the condition is true because for all point, there is at least one half plane while covering that point. So all points are covered. If on the other way around, there is one point, let's say this, such that no half plane covers that point, then the task set is not schedulable. For example, if you have half planes like this, half plane that is covering in this way, you have this point is out, and then you have, I mean, the task set is not scheduled. This is why it can be seen as a covering. Yes, because I mean here what I did was just to bring the ki on the other side. And here you have just a condition, a linear inequality on the k with these coefficients. This is a linear inequality on the k. The k are the variables. Right, and you have, this is just a condition. So if you, for all k, you always have at least one among these n conditions, and yes, that is covering, then you're satisfied. Okay, what else is here? Yes, right. Something that I want to highlight here is that if u is equal to 1, this linear inequality will become linearly dependent. If you compute the rank, you will find it out, but just, I mean, maybe there is a simpler way to show, but this is something that happens. Okay, basically, these lines, I mean, what is happening, maybe the next slide just illustrate that better. Yes. Now start with, yes, let's have this slide. Okay. Okay, so here I'm just an example where I have T1 equal to D1 equal to 4, and C2 equal to 2, and T2 equal to D2, 8, I mean, those values. If you compute, those inequality, the inequality which was written just here, if you know everything, here I consider just a physics, if you know everything, this, and this, then you can compute it. And then basically you have this condition, okay? Since I have dead and equal to periods, I have 0 on the right-hand side. You see here, there is minus Ti plus Ti. So if they're equal to, if they're the same, then you have 0. If you have 0, then basically the linear inequality goes through 0. Okay. Okay, and then basically you have to cover well, and all the integer numbers, well, the natural numbers square, except 0, 0, so we don't care of covering this point. And right, so we have condition for I equal to 1, which I guess is the uppermost, while for I equal to 2, you have the second one. And so you have, so minus 2, 3, so it is pointing like this way, so you have this half plane. So the half plane from this line and below correspond to the first condition. The half plane from this line and above correspond to the second condition. And so we can see that those values are fine, so the task set is scalable, as I hope is natural to see. 8, 2, 3, yes, it's quite do a quarter set, okay, because the total utilization is strictly less than 1, so it's 5. Total utilization is 1/2 plus less than 1/2, so it's strictly less than 1. Okay, right. So what I wanted to say is that now we said that we have this value up here and those values up here. When the utilization increase, what is happening is that these two lines start to become close to each other. When they are utilization is exactly equal to 1, these two lines are coincident. Are certainly linearly dependent, but if the dead ends are equal to periods, then they're just coincident, right? Maybe this is something I can show explicitly. If total utilization is greater than 1, strictly greater than 1, what is happening is that the two lines goes like, so this moves up so much, goes this way, and then it means that, even if it's a tiny bit, if the slope is different by a tiny bit, there will be always, the gap here will increase, and at some point there will be some integer far away in the future which will be outside, okay, and not covered. And in fact, if the total utilization is strictly greater than 1, the task set is not scalable. This is something we know. Okay? I just wanted to be a bit more confident. I just want to write this explicitly for a very simple case. For n equal to 2, and for n equal to 2, we get, for I equal to 1, we get C1 minus T1. Okay, and let's say also the case of, let's keep it there, just n equal to 2, plus C2 K2. And I equal to 2, we have C1 K1 plus C2 minus T2 K2. If total utilization equal to 1, I want to try to show you that these are linearly dependent. Let's see if I can manage. Okay, so if so I want to find right. So let me divide this by let's see, by T1, for example, and this by T2. I think it's quite natural to do. So you divide this by T1, this by T2. I get U1 minus 1 plus this by T1, yes, it's a bit ugly, so I have maybe T2 over T1, U2, T2, and T1. T2. And then here I have T1 over T2, K1, plus U2 minus 1, K2. Okay, let's see. If total utilization is equal to 1, then this is equal to minus U1. Minus U1. Yeah. No, qui c'era U1. U1. Yes, this is equal to minus U1. Right. This is equal to minus U1. Okay, so I take U1 away and I get T1 over T2. These are the coefficient of the second one, while the coefficient of the first one are minus 1, T2 over T1. And if I multiply these, yes, and these are linearly dependent, because if I multiply by minus, yes, if I multiply this by minus T2 over T1, I get the one above. Okay? I mean, you do it yourself. Okay, just to say that if utilization equal to 1, those equations are linearly dependent. Okay, what happens if we change the address? Let's say that we are in this case. So in this case, we have utilization strictly less than 1. Since the addresses are here on this side, changing the deadline is just changing the level, I would say, the level of the half plane. So from this condition, if we decrease the deadline, basically, I mean, decreasing D1 means to take this equation, this half plane, and move it this way. If we decrease D2, it means to take this half plane, that is up here, and push it up. How much can we decrease it? Well, we can decrease it. So here I'm decreasing what I'm doing. I'm decreasing the D1. Yes, here I'm decreasing D1 from this condition above. By decreasing D1, how much can I push it down? As long as I cover this point. Because if I push it further, then basically, yes, this point is not going to be covered anymore, right? So this point goes here, and then I cannot push it. Otherwise, this point is uncovered, and then the condition is false. So by putting this point into the machinery, we find that the minimum deadline is D2. The minimum deadline for D1 is equal to 2. Okay? In the other case, let's say we want to find the minimum deadline D2. Basically, we have to push this half plane up. How much can we push this half plane up? We can push it as long as this point is covered. Okay. And if we do this kind of trick over and over, what we find for that very special case, this space of feasible deadlines. So this corresponds to, let me write here, so I remember. So to the case of, well, I'm changing the data, so the I is no longer equal to 4, right? So it's T1 equal to 4, and C1 equal to 2, T3 equal to, that's 3, whatever. T2 equal to 8, C2 equal to 3. Okay? So the space of feasible deadlines for this case are these ones. Okay? So of course, D3 can never be below C3. And of course, D1 can never be below C1. This is obvious. Okay? It was also obvious that so deadline equal to periods are always good because here we have total utilization less than 1. So D1 equal to 4 and D2 equal to 8. Up here is feasible, it is, okay? Even a bit less, so basically we do, I mean, if we do this integer kind of things, we find it false. Okay? This, yeah, so this point corresponds to I mean, when I say that by moving this up here, D2 equal to 5, so this number 5 is the one that you find back here. So you see that D2 for these values cannot go here. Otherwise, what happened here? Actually, D2 can even increase, can even decrease even further. But what happened? To decrease D2 even further, you need to cover this point by this inequality. So if instead, if you increase D1 up to a point that you can cover this, so like by some amount this way, then D2 can be decreased a bit further. And so this corresponds to this kind of zigzag shape. Changing the periods, and now it's a bit more, yeah, so far it was quite simple.
Here, the condition is di is less than pi, or for otherwise also?
But the colleague here, the inequality?
No, I'm saying.
No, for any deadline.
For any deadline.
Any deadline, larger.
It's larger than pi?
Yes, even larger. Here, the periods were 4 and 8, but you know, this is condition which is true in general. So D1, 4, actually it has some advantage sometimes. If you increase the deadline of the task T1, so if you increase D1, you can gain in D2. It is something that may be useful. Let's say that D2 is very sensitive to jitter, and you want it to be very precisely scheduled. So you set D2 equal to its minimum value, which is its computation time. You cannot decrease D2 less than C2. So if you set, then you may ask yourself, look, if I have set D2 equal to C2, what's the minimum feasible value of D1, which I can tolerate? And it is 5, which is larger than the P.
But in this case, can you go to the main slide? That equation. Yeah, this equation.
Mm-hmm.
In this equation, suppose I am taking only one task. Only one task.
Mm.
And then C equal to 2, T equal to 2, and D equal to 3.
You're taking what?
C equal to 2.
C.
Computation time.
So only one task? Eh?
Yeah, only one task. I'm just checking whether it's
okay, checking only one task, it's easy, okay? Because
so in this case it's not
so for one task. Yeah. For all maybe one task it doesn't apply. Okay. So for all basically what does it become for one task? For one task is for all k into, let's say, right, the integer without 0, okay? You want that exists one value in the vector, but then now the value in the vector has to be that value, because only one. So now I is 1 and ki is k, such that, so now we have I equal to 1, and of course ki is equal to wk, such that what? The sum, such that C k less than or equal than K minus 1 T plus D. Of course, yeah. It is what it has to be, right?
Yeah. But this condition, like I'm checking with one example, if C equal to 2, T equal to 2, and deadline is higher than the this time period, then it is giving 0 less than equal to minus 1.
No. Because
no, not this one. The CI minus TI. Yeah, this.
Oh, let's see. Okay, maybe I don't know. I may have done some mistake. For okay, look, for one task only, you don't have this, right?
Yes, there is no.
Okay, so
CI minus TI.
Let's see. Let's
if CI equal to TI.
Yeah, 1 second. So we have C. We have only one task, right? So we have no I anymore.
Yeah, C minus T.
C minus T times K. We have no I, so it's less or equal than what? Than minus T
plus D.
Plus D. Okay, when you want this to be for all K? For all K.
No, this can be continued. I don't think it will. I check.
Let's see. What value do you want me to write?
C equal to 2.
2.
T equal to 2.
2 and D?
D equal to 3.
D equal to 3. Oh. 0 less or equal than 1. It's fine. I like it.
If it is a
0 less or equal than 1.
If it is a deadline is 3, or sorry, time period is 3, and deadline is 2.
Yeah, but then you increase it. But wait a second. Okay, so you have the period of 3 and deadline of 2. I think, Sunil, you are on the wrong path. But, I like to follow this. It's good to play a bit. So, and the computation time is what? 2. It is feasible, right? It is also times feasible. Why that? Because, yeah, meno negativo.
Oh, yeah, sorry.
Yeah, minus K less equal than minus 1. For all K, yeah, of course. For all K integers, right?
Yeah, I just forgot this PM.
Okay,
Yeah,
it's fine. Oh, it's good that some people tries a condition. No, it's good. Sometimes you see, yeah, it works. Somebody proved that. Who did the first proof? We never know. Nobody has ever seen the first proof. Okay, let's move on. Here, periods. Okay, what happened when we change the periods? When we change the periods, it's a bit, well, it's not tricky. I mean, the point is that in this equality, let's see, the periods appear. So while the deadline appear in that inequality only on the right-hand side, so it was somehow easy to determine the effect because it was just a shift of the same inequality. The period appears both here and here. So it's a bit trickier. So basically, it's together with a shift. I mean, it's kind of rotation, if you want. And if you want to find the points where it rotates around, where the point in n dimensions, let's say in 3 dimensions, the line or the condition around which it rotates, you just the way I do, I write here Ti prime and Ti second, and then I try to see what condition I get for varying T, and just what I find is basically this condition. So we find the Ki equals, so if you make the intersection of this for varying Ti, okay, Ti, and then you find this condition, okay, which basically gives the point around which it rotates. For n equal to 2, it's a bit simpler, because for n equal to 2, basically it rotates around, if you change T1, the half plane rotates around the point K1 equal to 1 and K2 equal to this value. And if you change T2, basically it rotates around the point K1 equals to this expression and K2 equals to 1. I have an example here to see it in practice. So if with these numbers you plug into the formula I showed you in the previous slides, you see that changing T1 makes the half plane rotate around the point 1 and point 4, which is this one. So when you change the periods, basically the half plane rotates around this point. When you change the periods T2, the half plane, the second half plane, rotates around this second point, 1.51. Okay. And then now one may be tempted to compute or to draw, if you want, the space of feasible frequency. So let me write it the inverse of the periods, as I think is often a bit simpler. So F2 equal to 1 over T2. It has, of course, to be into the EDF region. Okay, so 1 over 2, 1 over 5. It's gone, completely gone. Maybe I can, let me see if I don't reach because I need both. Okay, so this is somehow the EDF region of feasible task frequencies. I mean, this is just 1 over C1 and 1 over C2. This is just the EDF, the necessary utilization s equal to 1. Okay, now let's see what happened. Right, for values, I mean, starting from this value, I mean, now I want to move along this total utilization boundary, because as we know, if we go below, it's always good, because if I find a point good here, then everything is good here. So if I can, let's say, go through the entire line, then everything is good. Okay, let's start from this point. T1 equal to 27 and T2 equal to 27 over 5, which is a point that gives full utilization, and probably is a point like 1 over 27 and the corresponding point here. Okay, and here you can see, I hope you can see that, you can, since I'm moving along utilization equal to 1, I'm moving in a way that these two lines are always parallel. So when I move these two lines, I always cover everything. Actually, the points here, this point is covered twice, so I'm a bit I have some slack, if you want. Then at some point, at this kind of critical condition, I have the two lines aligned together, and this corresponds to the case with T1 equal to 8, which is maybe here, so 1 over 8 is the frequency, and T2 is whatever you get from here. Okay, then from this point you can actually decrease T1 a bit more, or increase F1 if you want, because you can leave some white space here where you do not cover, as long as, because the integers are not covering the entire real plane. So you have some space between integers, and if you do the math, the maximum you can do is this. And then from this point, then basically you will find some holes. Okay, so 1 over 6. But then from this point and on, for example, here is somehow dashed. So there are some points which are not covered. But then this point is also covered, and then if you go on, there are Once in a while, you find points that covers, but then there are some points where you do not cover. So here is a bit unclear what it looks like. Okay. Yeah, I just go on and we conclude. I mean, 3 slides and we finish. Of course, I mean, this kind of well, this visualization is right. I mean, the condition that I presented before is exact. So, I mean, there is no big further investigation. That's the way it is. So, however, I mean, this way it is may complicate pretty much if you want to do optimization. Let's say that you want to assign optimal periods. I mean, how do you run optimization of a region which is like this? We don't know. It's a crazy way. So one good way to go could be to use sufficient tests, of course, right? So there was this test, which is a sufficient condition for ETF, which, for example, has the advantage of being convex in the space of delta. So if you have a function which is convex also with the deadlines, then you can very efficiently solve the optimization for the deadlines onto this region. And to give you an idea of how this region looks like, basically, if this was the space of exact feasible deadlines, the region, the convex region that you get from the condition just before is this one, okay? Where basically you cut this corner, which are the source of this non-convexity, and then you may do optimization onto here. Optimal design, yes, I'm about to conclude. This problem, the optimal design of period and data, is very typical in control systems. For example, in control system, you may be given computation time of tasks, which have to run onto a controller or whatever device which have to control. And the idea is what is the best choice of periods, sampling periods, and deadlines, which in this case correspond to the delay from the release to the completion, such that some metric is minimized, some cost is minimized, or performance. Okay? And such that it's scheduled. Okay, this problem is very difficult, solving jointly period and deadlines. What I want to say is that there are some cases where, well, let me show you this example. So suppose you have computation of 2 tasks, right? Computation time C1 equal to 1 and C2 equal to 1 again. And suppose that you run optimal periods, and you find that your optimal periods are something like, typically optimal periods are always fully utilizing the processor. It is quite typical because there is always a gain in performance by running the controller faster. So it will never end up with periods which are not fully utilizing the processor. So let's say that from those computation times you get these values of periods. However, from the space of deadlines, we know, or at least we understood that if you have periods which are values such as, let's say, bad values, 2.1 or 1.91, the amount of reduction of deadlines that you can do is very limited. And the amount of the data reduction is the amount of separation of those planes, right? If the periods are very bad, like in this case, the amount of reduction that you can do is very little. If instead you take, let's say, periods which are not optimal for periods, but which has the advantage of being the same, for example, T1 equals to T2 equal to both 2, so they are both equal to 2. In this case, the amount of reduction of deadness that you can do is much larger. So if, for example, the task set is very sensitive to the delay, maybe it's more convenient to assign suboptimal periods if this can lead to a greater cost reduction in terms of delay, because you can make data very, very short. While in this case, the data you can really not touch. Okay, this was the last slide. And yes, and of course, yes, solving this problem would be a decent contribution, because here we are somehow suggesting not to choose the optimal periods, because the optimal periods are these ones, but then we see, look, if we just perturbate the optimal periods by a little bit, instead of 2.1 and 1.91, we take 2, we lose optimality for the period, but we gain a big advantage in terms of data. We can reduce the data by a lot, making possibly the cost smaller if the task set is sensitive to the delay. Okay, this concludes the class. We conclude it also for the.
Can you please say what the cost is?
The cost is the cost.
Like for example.
The control cost, the inverted pendulum, the amount of deviation from the stable position of the inverted pendulum. Okay, let's say that of course you want the inverted pendulum to stay as vertical as possible. If you deviate, and you can somehow, not somehow, you can write that as a function of the period of the controller. You can write that as a function of the period of the controller. And you can see that, with larger periods, the cost is larger, and if the period is smaller, the cost is smaller, so on and so forth. Okay? Va bene.